Okay, so the topic for today that we will get to is visualizing uncertainty. Okay, and but we still have to finish up some slides from last class. All right, so our agenda for today, we're going to finish up on our plot refinement stuff, and then we will talk about common ways of visualizing uncertainty and how to implement them in ggplot. Okay, from there, like sort of the main thing that we're going to talk about is framing uncertainty in terms of relative frequencies rather than probabilities. Okay, we will talk about probability some too, but probabilities, as we'll see, are sort of just difficult for us to interpret. We'll talk about standard errors and a few non-standard ways of visualizing standard errors. And then we'll talk about these things called hops. And I realized right before class that this is cut off, so I'll try to fix that after class, but it's not that big of a deal. So these things called hops, which stands for hypothetical outcomes plots, okay? And those are very often animated. So we'll look at those, and I'll show you a quick way to create a couple of those. And related to hops, we'll talk about bootstrapping as a way of, actually it's a way of estimating standard errors, but you can use it for visualizing standard errors as well. Okay, so on the agenda today, we're going to finish what we were talking about last time, and then we're going to talk about visualizing uncertainty. Assuming we still have time after both of those topics, which I think we will, then I'm going to at least introduce tables today. Okay, my hope is that we can get all the way through tables. We may be able to do that, we may not. So I guess we'll just see how it goes. Okay, and then assuming we get to tables, we're going to be talking mostly about a package called GT. Okay, so you can install that package now. If you want, I will be asking you to be following along a little bit. We'll be creating a table. We'll talk about formatting columns, creating spanner heads, and a few other things. Okay, and then if you choose to, then we will also so let me back up. We will also talk about fonts if we have time. I doubt we'll have time today because I'm not even sure we'll get through tables. But if we do, we'll talk about that as well. And then, so if we do that, then you'll know some ways to implement more fonts if you so choose. Okay, and I would really encourage you actually to play around with fonts a lot. They can absolutely be this rabbit hole that you just like never come up from. So be careful not to do that. But it's if you haven't played around with fonts much in the past, it's amazing how much they can change the look and the feel of the thing that you're creating. Okay. So next week, we're going to talk about HTML, basically. Okay, so next week, we're going to talk about creating data dashboards, creating a website / blog, okay, and then basically taking your final that you're working on and putting it in that sort of a format. And when we do that, we'll talk a little bit about CSS, cascading style sheets, which is a way to basically style your HTML. And the reason I say all of that is because fonts become very important there as well. Okay, so you can import all sorts of different fonts if you want. So if we don't get to fonts today, we'll get to fonts next week when we talk about that stuff. Okay. So the expectations for today, this is similar to last class where we don't have like a homework or a lab that we're going over because the homework still isn't due for another week. I hope most of you have at least started on that. I know that there are parts of it that we still haven't gotten to, like the first one says recreate this plot. Most of you should be able to basically do that, but maybe there's some challenging aspects to that, and we'll talk about it today. But then the second one is, reproduce that plot again using a non-standard version for visualizing the variance or the standard error, right? And we haven't talked about that at all. So hopefully you have started on it some, and like when you get to that part, you could just skip it and go on with the rest because there's other parts of it that we have talked about. But that is due 1 week from today. So after that, we'll go through that and etc. Okay, we're a little bit behind where I'd like to be at this point in the term. So that's just where it is, where we are. So I'm hoping that we can, by using a little bit of week 10, we can get through everything, but we'll see how it goes. Okay. And then just a very quick warning. It's not like that big of a deal, but I do just want you to be prepared that today is a little more stats heavy than basically any other topic in the first 3 courses. Okay. So that's just a little bit of a warning. It's not like super heavy, but just a little bit. Okay. So before we get to any of that though, I did want to have us finish up plot refinement. Okay. So that is over here. Okay. So the first thing I wanted to talk about is saving plots. Okay. And remember, I've talked about this a couple of different times now, but you might, most of the time when you're saving a plot, it's just because you're ready to save the plot. And so you want to output it because maybe you're going to give it to a colleague who's going to incorporate it in their paper or whatever. But very often, well, not very often, sometimes you want to output that plot because you want to do additional annotations to it. And it's easier to do those annotations outside of R. Okay, so in all of these slides previous, this was last class, right? We talked about all these different ways to annotate plots where we could, you know, highlight specific points with little labels that call out the text for them or whatever. We saw with ggforce how you could kind of circle groups of plot or groups of points and things like that, right? With bar plots, labeling the end of the bar or the inside of the bar with the actual number that the bar represents, those sorts of things, right? But occasionally it's just a lot of finicking where you're like messing with it, where you're like, okay, 27.3, nope, that's too far left. 27.8, okay, now that's too far right. 27.6, and then you get all the way done, and then you go to save the plot, and you save it in a different aspect ratio, and then you're right back at square one again, where you have to do this over again, right? And so we talked about that GG preview function that's really super helpful and useful for previewing things in the aspect ratio and at the actual size that you'd be outputting it, right? So that is still generally my process. However, there is nothing wrong with making additional annotations after you've saved your plot. The only problem with it is that it ends up being less reproducible. So I could see something in your GitHub repo that I run all the code for, and my plot doesn't end up looking exactly like yours because you've done additional annotations after the fact, right? If you look in the syllabus, I talk about that exact thing, and I note that that is the one exception to reproducibility that is acceptable, okay? So I'm going to, for your final projects, I'm going to clone your repos and I'm going to try to reproduce everything that you have displayed, right? And assuming it all looks like yours does, you'll get those points. That's 90% of the time at least, okay? However, if you've made additional annotations outside of that, then I will be able to figure that out probably, but it would be good for you to just drop me a line and say, hey, I did these additional annotations after I saved my plot, and then I'll know, and then we'll be all good, okay? So when we're saving plots, there are 2 basic ways that we can save a plot. We can save it to what's called the raster or bitmap format, or using vector graphics, okay? So we'll talk about this exact same thing again a little bit in about 2 weeks when we talk about mapping, creating geographic maps, because this is the exact same principle there, okay? So raster, also called bitmap, stores everything in pixels. So everything is literally a grid of colors, right? A grid of, like, you take the plot and you cut it up into a grid, and then you fill in each grid with a specific color, basically, okay? Vector graphics function completely differently. Vector graphics actually have instructions inside them that tell the thing how to create the plot. So, you know, at this top left corner, there should be a curve, and at this part, there should be a straight line, etc. Okay, so vector graphics, when you resize them, they are redrawn every time. And that has substantial benefits because they maintain a perfect picture of what it actually looks like. Okay, so here's an example where we have this ridgeline density plot in that A version, and then B is stored to a bitmap or raster, right? And C is stored using vector graphics. And this is from Wilke. But you can see in B, it looks great here, but you start to zoom in and you can start to see some distortion there, okay? Whereas with the vector graphics, you can zoom in however far you want and that line still looks absolutely perfect, okay? Because it's actually being redrawn as you zoom in, okay? So there's gonna be zero distortion at all. Some common vector graphics are PDF, EPS, which isn't super common, and SVG, which I would say is probably the most common outside of PDF, all right? For raster graphics, you have PNGs, JPEGs, TIFFs, and GIFs. So these are all ones I'm sure that you've heard of before, right? There are, however, having said this, some pretty significant downsides to vector graphics, okay? The main thing is they can end up, which is actually my second bullet point, they can end up being really, really large. So if you have a super complicated figure, it's got all sorts of points, like maybe it's got 10,000 points in it, right? If you're going to resize that thing, it's got to redraw all of those 10,000 points. And so it ends up being a really large figure and it ends up being not very portable, okay? The other thing that is less of a problem in my experience, but I know it is an issue, is that it's possible that they can look different on different displays and different software, right? So it could look great on my computer, I give it to somebody else, they open it up and it looks slightly different and maybe skewed in their computer, right? Or similarly, maybe I have it open with my web browser and it looks great, and I open it in, you know, whatever, Microsoft Word or something, which I wouldn't open a figure with Microsoft Word, but you know, some other program, and it doesn't look as good. So those are the downsides to vector graphics. For bitmap, or raster, you have to, when you have alternative versions of how you can store it, okay? One is called lossy compression and one is called lossless compression, okay? So lossless guarantees that that image, pixel for pixel, is going to be identical to the original. So you have some original figure, it's like this big, right? And then you save it to a different size usually. So maybe you save it like this. If you use a lossless compression, it is going to guarantee that that image is going to look exactly the same pixel for pixel, okay? So Ping and TIFF use lossless compression. Lossy is going to reduce the size of the image pretty considerably, but because of that, it's going to basically accept minor artifacts and minor sort of distortions to the image as it goes down. Okay, so JPEG is probably the most common lossy format. So this is like a lot of background, but it all leads to this practical advice. Okay, if you are going to be saving in, like, you're going to be using Word, Microsoft Word, or whatever, then just export it to PDF. Okay, if that won't work because you're doing something on the web, PDF actually will work on some web browsers and everything, but we don't really want to do something that will work in some cases and not in others. So if you're using it for the web, then use Ping, okay? And Ping is a lossless compression. If for some reason that won't work, like the file size is still gigantic, then go to JPEG. So that's like your last line of resort, okay? So this is the way I typically do it, and this is also how our book recommends it. Export to PDF. If that won't work, export as Ping. If that won't work, then look at this lossy compression one, so JPEG. Okay, so we're going to practice here for a minute. What I'd like you to do is create a plot, and I forgot a timer on this one, so I'll just do it on my phone. We're going to create a plot. Any plot you want. It shouldn't be a super complicated one. It should be one that you can create in, 30 seconds, maybe. And then I'd like you to save it as a PDF using ggSave, okay? So the first argument to ggSave is actually the path where you want to save it, okay? So for me, I tend to set up my R projects where I have the R project is root directory. I usually have a data folder, a scripts folder, and a plots folder, right? So I would say ggSave, and then I'd say here, plots, myfig.pdf, okay? So this is exactly what I'm talking about here. Saying here, myplot.pdf, that would just save it to your root directory, wherever that is, okay? By default, it's also just going to save the last plot that you created. So you could say ggplot, call a bunch of different plots, and it's just going to save the last plot that you created. If instead you want to save a specific plot, that's the second argument, okay? So you could create a plot, call it P, and then create a second plot, call it P1, or let's say first plot is P1, second plot is P2. Then you want to save P1, right? You could say ggSave here, myplot.pdf, comma, P1, all right, and give it that object that has all of the stuff in there, okay? I also don't have this in here, but there are different width and height arguments as well as a bunch of other things. So go ahead and play around with that as well. Change the width and the height and save your plot, okay? I'm saying to create a PDF. If you get through that and you're feeling good, then try to go ahead and just save it as a ping or a JPEG too, okay? So I'll give you about 4 minutes for this, and then I'll walk you through it myself. Okay. So let me switch my share here. We'll go to RStudio. Okay. So this is what I did. Let's go. Just ggplot should do it. Okay. And so I have putting with the MPG data set, I'm putting engine displacement on the x-axis, highway miles per gallon on the y-axis. And then when I create that plot, it looks like that. Notice I'm using gray 80. And then I'm highlighting 4 cylinders, maybe. Oh, yeah, I need to go dplyr. Okay. And so that highlights the 4-cylinder plot, right? Because this was the last plot that I created, I can just say ggSave and then give my path. In this case, I'm not actually saving it to my directory. I'm saving it to my desktop, so I just put a hard-coded path. Again, I would not recommend that you do this generally. This is something that you can do for like temporary files, but it's not generally what you're going to want to do. Usually you're going to want to use here, okay? I'm going to also just add theme, pull this out. Theme, minimal, and I'll make the text size a little bit bigger at 15. Okay, so there we go. All right, so I'm going to say ggSave. I'm adding these additional arguments. Width is 6.5 and height is 6.5. Okay, so I do that. And then on my local, on my desktop in this case, I have an object which is called preview example plot.pdf. Okay, and it looks just like this. So that's cool, right? It's a PDF file and it's the width and height that I want. What if I change those though? So I make the width, 8.5 and the height only 3.5, right? Then that really changes what this thing looks like, right? That's the aspect ratio. That's the thing that we've talked quite a bit about at this point. Okay. Any questions on that? Okay.
I have a question.
Yep.
Will this only work if you use ggplot to make graphs?
ggSave?
Yeah, because I just did like plot and then pressure in parentheses, like the default one, and then did ggSave. And when I try to open it, it says that I get like a message saying that it's like a corrupt file or something.
Yeah. Yes is the answer. ggSave will only work for ggplot objects. And the reason is because base graphics and ggplot are based on 2 entirely different graphing systems. So the base graphics are based off of the base graphing system. There's no other word for it. Whereas ggplot is based off of what's called the grid graphing system. And grid is also part of base R. It's just not what's used for the base plotting system. And it's much, much more complicated than the base plotting system, but it's much more powerful as well. And so that's why ggplot is built on top of it, is basically to make that really powerful plotting system more accessible to you than it would be otherwise. Okay, so let's go back to the slides for a second. Let me go here. Maybe I can just do it like this too, because I'm going to come back here for a second. Okay, so let's say now I have that plot saved and I want to do some modifications. Okay, I mentioned that I don't do this super often, but one tool that you can use that is free is this one called Inkscape. Okay, and so I'm not super facile with this, but it is very powerful and it can do pretty much everything that Adobe Illustrator can do, and it is free. So that's the one that I would recommend. There are other options out there too. And if you have a paid software to do this like Adobe Illustrator and you already feel comfortable with it, then go ahead and do that. Okay. But what I would do here is I would basically, I'm just going to share my entire desktop, even though that doesn't always look the greatest. Okay. What I would do here is you can see I have this example plot.pdf here, and I would right click on that and then say open with, and then I'd say Inkscape. Okay. And this will take a second. It's not like the most user-friendly program, but like I said, it is pretty powerful. So we'll just say okay. And oops, that's not what I meant to do. Stop that. All right, so I'm gonna pull this like this. I'm gonna put this back to 0. And then there we go. All right, so now I can do things like, you know, maybe I want to take this and I want to circle these points, right? That's really bad, but you get the idea. And then I could change the color of that. So let's see, I could go like right click on that and go fill and stroke. And I want to go stroke and change this to maybe that green color or whatever. Okay, and I could also obviously adjust that, but then I can take a text box, put it right here and say, these points are cool. All right, that's obviously not a real like annotation, but you get the idea. And then you could save it, and you could then save it as a SVG. But you can also save it as a PDF again. Okay, so let's see. Yeah, so now so let me quit out of here. And now it's asking me if I want to save it as an Inkscape SVG, and I'll say, yeah, sure, let's do that too. I'll keep it on the desktop, right? Example point SVG. And then we can come here, and now you can see we've got the SVG here, but we've also got this example plot here. And if I just preview that, you can see the annotations we made are there. This is one that I saved just to give a little bit of an idea of something that you might actually do, right? This still could obviously be better, but this took me like 5 minutes because I don't know this program very well. But still 5 minutes might be a lot faster than doing it in R with ggplot. Okay, so that's just another option of something that you can do if you want to. Okay. Any questions on that? Okay. Okay. Compound figures. So ideally, I would like you to follow along on this. This is the same sort of thing that I just talked about with that infographic. Okay. So my favorite is a package called Patchwork. This is, again, Thomas Lynn Peterson. He's the same guy that did ggForce, does a bunch of other ones. Everything he does, basically, I think is amazing. He's one of the authors on ggplot now and works for RStudio. Okay, so if you don't already have this package, go ahead and run install.packages patchwork. And while you're doing that, I'll kind of just keep talking here. There are a number of other packages that do similar sorts of things. So I think I have mentioned before the package CalPlot. CalPlot is also a very neat package. It does a lot of annotation sort of things, as well as a bunch of other sort of just ways of assembling plots that is nice. ggpubr is another nice one. Occasionally it works better for sticking two plots together. And then Grid Extra is sort of more of a legacy package. It was probably the first package that I know of anyway that made this sort of thing doable. But since then, it's much easier to use some of these other ones. Okay, so first, you can actually just go ahead and copy this code right out of the slides, but I'd like you to go ahead and create both of these plots. And notice on both of these, I'm actually saving them to objects, right? So the first one is a plot that I'm saving to the object P1. Second one is a plot that I'm saving to the object P2. Okay, so P1 has engine displacement on the x-axis and highway miles per gallon on the y-axis, and then it has points there and a geom smooth layer. Okay, the second one is a box or a box plot. Sorry, where we have the number of cylinders along the x-axis and then the highway miles per gallon on the y-axis. Okay, so we're going to have different box plots for each of those. Okay, I'll give you another 10-15 seconds just to copy that code and get it going. Okay, if we wanted to put these plots together, we can put them side by side actually very easily with Patchwork. All we do is call library Patchwork, and then we can just say P1 plus P2, and it's going to put them together in a single figure. Okay, so go ahead and run that code, and then give me a thumbs up if it's working for you. On Zoom, if you can give me the emoji, that would be good. Great. I saw one person. Is it not working for the rest of you, or are you just not responding? I guess is my question.
Still working on getting the coding.
Okay. That's helpful. Thank you. I'll give you another 30 seconds to make sure that you have the time. So 30 seconds starting now. Okay. Hopefully that was enough time. When we're putting these together, though, you might think, well, okay, that looks fine, but like it would be a lot better if we didn't have this giant space between the two of them that is taken up by that legend, right? Like maybe I want the legends both just on one side, right? And we can do that very easily. All we have to do is say plus plot layout guides equals collect, okay? And so what that's going to do is no matter how many figures you have in there, in this case we only have 2, but you could have 52, it's going to take all of the legends from them and it's going to stack them all on one side of the figure. Okay, so that looks quite a bit better, I think, in this case. The other thing we might want to do is instead of having them side by side, we might want to stack them vertically, okay? And so in this case, all we have to do is instead of saying P1 plus P2, we would say P1 divided by P2, right? So you can think of it just like equations, basically. And so this is going to stack them vertically, on top of each other, and then I still have that plot layout guides equals collect. Okay? Let's say now that I have a third plot that I want to add in. And again, you can just copy this code if you want. And this one is going to be a bar plot for average miles per gallon for each manufacturer. Okay? So here I have this third plot that I want to add in. And I can do it like this. Okay, so in this case, I'm going to have the first two plots, actually the first and the third plot on the top, and I want the second one on the bottom. So I can just surround them in parentheses, P1 plus P3, and divide that by P2. And notice that P2 takes up the entire space filled by P1 and P3. Okay, so to me, this is like pretty exciting because it's a pretty powerful way to make this compound figure with code that I think is pretty intuitive and pretty simple, but very powerful. Okay. We can also do some additional annotations. So here, this is super common, right? We might want to have a title for the overall plot because we've made this compound figure, but now we want to have a title for the overall figure, not for each figure, right? And so we can do that by saying plot annotation, and then the first argument to that is title. There's also subtitle, and there's a few others like caption and things like that, okay? So here I'm just saying some cool plots. The other thing that we might want to do that's pretty common is add these tags to it, okay? So if you look at the documentation, it'll help you out here a little bit in terms of how these tags are going to fill out, right? But here I say tag levels equals, and I have a lowercase a, okay? And that's going to make them A, B, C, D, E, F, whatever, okay? If I used an uppercase A, it would do the same thing, but they would all be uppercase. If I used I think it's the digit 1, then it would just count them 1, 2, 3, 4, okay? And I think there might be one or two other options. All right, but that's a nice way to do it because then you've created this compound figure, and then in your paper when you're writing it up, you can say in figure 3B we have a bar plot, and in figure 2C or whatever we have a box plot, and describe it, right? The last thing that we might want to do from this, and this is exactly what we saw in that infographic, are what are called insets, okay? And so this is where you have a single figure, and then you're going to literally insert another figure into that figure, okay? So we do that through Patchwork with this thing called inset element. And this is not as straightforward as the rest of it, right? In terms of just like stapling plots together, that's pretty straightforward. This is less straightforward, all right? But it still hopefully is fairly, it's doable, right? It's not quite as easy, but it is doable. So in this case, I'm creating this P3 small text because basically I just wanted to reduce the size of the text for this image because I'm going to put it inside of the other one. And so the text was so big before that all of these labels were overlapping on top of each other. This is also very small at this point, but who knows how big we're going to output it, right? We could be outputting it huge. And so what I'm going to do is now this is the figure I want to insert into that figure. And so I'm going to say P1, my scatter plot, plus inset element. Okay, so inset element, it's going to say, okay, I'm going to insert a picture I'm going to insert a plot into P1. And then I'm going to say P3 small text. That's the one I'm going to insert, right? And then these next arguments are just where on the plot do you want to insert it, okay? And so these arguments go left, bottom, right, top, okay? And so these point, like 1 and 1 is like 100%, right? And 0.6 is like 60%. You can change these and play around with it, and you'll see how it changes where it's at on the plot. It will also change the size of the inset depending on what those values are. So this is a little bit finicky, right? And this can be tricky to get exactly right. This is also another place where I really highly recommend you use that GG preview function so that you're outputting it in the aspect ratio that you want. And then you're using this inset to make sure that it's popping out and it's appearing where you want it to be in there, given your aspect ratio. Okay? Any questions on any of that? Yes. Yes, because it's the exact same plot that we have here. All I've done is I've said for the text on the y-axis, make it size 8, and for the text overall, make it size 8. I don't remember why I had to declare that twice. It should have been just once, should have worked, but for whatever reason, it wasn't working, so I declared it twice. Yep. Okay, last thing. This tends to be something that people spend a fair amount of time on, and it's not really my favorite topic. I think all of this stuff that we've talked about previously is actually much more important in terms of making your figure readable and interpretable and reducing cognitive load. But themes can be kind of fun, and they're basically just how do you style your plot, right? And so here's a couple different examples. This is the same exact plot, right? But shown with 4 different themes. Okay. And so my slides are being really slow here. So how do we do this, and what themes should we be looking at? Okay, GG Themes is a package that is a good place to start, I think. You have, if you go to this link, you will see a whole bunch of the different themes that exist. Okay, and all of these are available to you once you install and load the GG Themes package. Okay, so you can see, so you can look at them there. I have this joke about, you can fit in an economics conference with themes data. There's a whole bunch of themes in there that are meant to basically mimic other software, which I think is sort of an odd goal, but like there's Theme Excel. I don't know why you would want to do that, but some people want to, right? And that's cool. 538 theme, it's kind of nice, right? So some of these, like I could understand wanting to mimic that theme. Not really Excel, but maybe some people like that. So you can look at those and check that out. That's a good place to start. There's also the BBC. I have links here to their repo. They also have this journalism cookbook, which is really nice. You could probably read the entire thing and it would all be good. It's I've actually considered making it part of the required course reading. It's very good. Here, we'll go to it real quick. It's not very long. It'd maybe take you an hour or 2 to really go through all of this, maybe a couple hours if you went through it all really, really closely. But they just talk about why they use the style guide they do, etc. Okay, and for our specific class, we're going to use the USA Facts style guide if you're competing in the competition, right? And so I don't know that I actually have access to it right now. I'll make sure that I get access to it and get it to you soon. You don't have to have it in the USA Facts style by the time you present, but if you want it to be featured on their website, you'll have to make modifications after the fact to get it into their style, okay? And that's really all of this stuff is style. But here's another example from the BBC. Really good compound figure. And actually, I think this is multiple figures that they've just put together. This looks like one, this looks like a second, and this looks like a third. That's still pretty nice. There's also this package called GG Theme Assist. It can't do everything, but it can do a lot of things. And down here, basically what it is you create a plot, and then you run through the add-ins GG Theme Assist. It's going to create your plot here, and then you can, make all of these different modifications to the theme that you want here, like this. And then when you're done, you just say done there. And then, so basically gives you a GUI to interact with your plot this way and change the way it looks and feels. When you say done, it will actually paste all of the code back into your console to do that. Okay, so so it's not like you're cheating and you're not writing the code. I mean, you aren't writing the code, but who cares? You're getting the code that you need there, and that's all that really matters for like reproducibility, etc. Okay, so that's another kind of fun one. I would check that out. I used to use that a lot. I almost never use it anymore, but it's a good place to kind of get started on a lot of that. And then after that, if none of those things are getting you exactly what you want, well, then it's time to jump to the theme function. Okay, I've talked about theme quite a bit. You've seen me use theme quite a bit. It's quite a bit more complicated. As I've said, I've used ggplot for years, and I've really only in the last like maybe 2 to 3 years gained any sort of fluency with it. It makes sense once you sort of understand the logic of it, but it's complicated. Okay, so that's what part of why I recommend using that GG theme assist to start. Okay, so quick example from lab 3, I created a plot that looked basically like this, right? And this is I stored this in an object called P, and then I added all of this theme stuff, right? And then that gives it this dark theme that I ended up using. Okay. So again, not the most important thing, but can be fun. It's really to get, most of the time, it's to get your plot to match with wherever you're publishing it. So if you're publishing it on your blog, you probably want the theme of your plot to match the theme of your blog. If you're posting it on somebody else's website, you probably want to use a theme that's going to match their website, etc. Okay? Any questions on any of that? I usually do not, but a lot of people do. And if there are common elements that you're using a lot, then yes, I would recommend going. We saw how to create that box plot theme. I'd recommend doing something like that. The other thing that we can do, if you have a bunch of themes that you're ending up using, you can create a tiny little R package. It's really not that much work actually to move from like a just functions that you're sourcing to moving to an R package that you're actually loading and hosting on GitHub. So that would be what I would recommend. Okay, let's go ahead and take about a 5-6 minute break here, and then we'll get started with visualizing uncertainty again. Okay? So I'll give you 5 minutes and 30 seconds, just because that's where my clock is at. Now, we're going to move on to uncertainty. Okay? So, the learning objectives through this are just basically 2 things. Okay? Understand that there's lots of different ways that you can visualize uncertainty, and the best way may often be what I refer to as non-standard. And what I mean by non-standard is just not like the typical ways that you generally see people visualizing uncertainty. Okay, and then from there you should understand how to implement some of the basic methods. Okay, with ggplot. So the primary problem just with all of this, right, is that when we see a point on a plot, we interpret that as the value, right? When in reality, that is an estimate or it's an observation or whatever. And so those points essentially always have some degree of uncertainty around them. That uncertainty might only be measurement error, but measurement error can still be fairly considerable, right? So I just want to show this short little clip. We won't watch very much of it, but there's this guy, Matthew Kay, who does this is like a huge part of his whole research area is on visualizing uncertainty. And I think this part of this talk that he gave, I would really encourage you to watch the entire thing. It's actually part of the required readings, but I know time is short always. But this is a very good talk, I think. I'd like to start with is this question, which is what happens when we ignore uncertainty. This is one of my favorite examples of an uncertainty visualization.
This is from a scientific paper. This is actually from recommendations for how scientific papers should be written. A mixed design ANOVA with sex of face as a within subject factor and self-rated attractiveness and oral contraceptive use as between subject factors revealed a main effect of sex of face, F of 1, 1276 equals 1372, P of less than 0.00, no thanks. So an alternative to this might be something like a regression coefficient table. You have essentially the same information there. The standard error is in brackets and there's probably some asterisks for p-values, although that's really not very great either. So you might line up all of your coefficients and do a coefficient plot and slap some confidence intervals on there. Essentially the same information is being communicated by these two presentations. You may even go a little bit further and do something like add a likelihood or a Bayesian posterior on top of that. So that's trying to give you a sense, a greater sense of the fidelity, or a greater fidelity in the sense of what the uncertainty in that estimate is, though. You still might ask the question, how easy is it to ignore the uncertainty? And I would argue very, so I could look at that number or that dot or that other dot and simply take those as the estimates and ignore the uncertainty. This contributes to what statistician Frank Harrell likes to call dichotomania, the unending ability of human beings to dichotomize things and ignore uncertainty. So what happens is I take all of these intervals, well, I won't try a laser pointer, or I can do it up here. I'll take all of these intervals that didn't overlap 0, and I'll publish those, and I won't publish that one, and then we get publication bias. So this is a problem. We talked a little bit about elections yesterday, and I think one of my favorite examples of dichotomania comes from elections. So these are probabilistic predictions of Trump's chance of winning the election in 2016 from 3 different poll aggregators. So 538 gave him a 28% chance, the Upshot gave him a 15% chance, and Huffington Post gave him a 2% chance. A lot of people got angry at these poll aggregators because they were surprised, and also for other reasons, obviously, but I think surprise was a component of it. And part of that is that you see that 28% and you're quite content to round it down to 0. So let me show you something else. This is called a risk communication theater. The idea here is I give you a ticket to a random seat in this theater. The seats are colored black in proportion to the chance of Trump's winning the election. I hope you might agree with me that you would be a little less surprised to end up in a black seat here than when I just told you the chance was 28%. So I think the lesson to take from this is that people are very good at ignoring uncertainty, but
that's basically what I wanted to stop at. So to me, that is like a very powerful thing to say, because this is very common, right? You hear 28% and humans just generally are very regularly going to say, oh, well, it's not going to happen then, right? Whereas like 28% is better than 1 out of 4, right? 1 out of every 4 times. And so those plots that he called, showed, which he called risk communication theater, that's a way of sort of communicating the 1 out of 4 frequency instead of just a probability that we round down to 0 or up to 1. That's the other thing. Okay, so we're not great at understanding probabilities generally. We very regularly ignore uncertainty even when it is there. And we very regularly round probabilities either up to 100 and say this is certain to happen because it's 91%, or down to 0 where we say this is certain not to happen because there's only a 17% chance, right? So we're not very good about interpreting probability generally, but as it moves to the tails, we get particularly bad because that's where we go to those extremes of it's certain to happen or it's certain not to happen when that's not actually true. So how do we typically communicate uncertainty? Well, he showed some of this, but I would argue the error bars are by far the most common way, right? We have a point, and then we want to talk about the uncertainty of that point, and so we use error bars. This is not to say that error bars are terrible and should be avoided. That's not what I'm trying to say. I think for specific types of audiences, specifically scientific audiences, error bars can be fine. However, I would also argue that even amongst scientific audiences, we still pretty regularly just ignore those error bars, even if they are there, and just interpret the points. okay? Or we do what he was saying, which is we only look at the error bar to see if it's crossing 0, and otherwise we ignore it, okay? But again, as I was just saying, that doesn't mean the error bars shouldn't be used. They are absolutely appropriate for specific audiences, specifically scientific audiences. Outside of that, I think most people are going to have a hard time understanding what you're trying to communicate with an error bar. But we still need to know how to implement them, especially because they are so common, and and so we're going to be expected to use those at times, right? So if we were going to do a vertical error bar like we just had in ggplot, we would use geom error bar, okay? So this is going to require two aesthetics that we don't have without calculating them ourselves, okay? They are the y min and the y max values, okay? So the minimum value of that error bar and the maximum value of that error bar. Those are not calculated for you, so you have to supply them. If you want to instead have horizontal error bars, so like you've got a continuous variable on the x-axis and you want a horizontal error bar, then you just use geom error bar h, right? With the h meaning horizontal. And then this, instead of having y min and y max values, you're going to have x min and x max values. So here's a quick example. You can follow along if you'd like. I'm not going to force you to, but I would like you to. So I'll give you some time to do that if you would like. So this is from, again, the MPG data set. So you can just copy this code if you want to follow along. But I'm calling this MPG by man because it's the average miles per gallon for each manufacturer. Okay, so I'm going to take MPG, I'm going to group by manufacturer, and then I'm going to summarize, and I'm going to create this new column, which I'm calling mean city, which is going to be the mean of the city miles per gallon. Okay, and that's going to give me a mean for every manufacturer. And then the standard error of the city, this is the standard error of the mean, right? So this is the standard error of the estimate, the mean being the estimate. Okay, and so we do that by taking the standard deviation of the city and then dividing that by the square root of the number, right, of the number of observations. So that there's a function in dplyr that's just n, and that will give you the number of observations. And it works really well in things like this, where you have a group by, right? So I've grouped by manufacturer. That n is going to give me the n for each manufacturer, which then helps me in this calculation of the standard error. Okay, so then we end up with a data set that looks like this. Here's the mean, and here's the standard error of the mean for each of those. Okay, and if we wanted to plot these, I'm starting with vertical error bars, right? We would take this, and I like, again, this is what I have argued throughout the term should be your default. If there is no implicit ordering of manufacturer, as there isn't here, by default, it's going to be in alphabetical order. But that doesn't really matter. There's no one way it should or should not be ordered. So I would order them according to the other axis, right? So in this case, I'm going to say, okay, factory order manufacturer according to its mean city value. Okay, and then I'm going to go ggplot, put manufacturer on the x-axis here, mean city miles per gallon on the y-axis here, and then I'm going to use geom error bar. Now notice my y min and my y max values are not just the standard errors, right? I'm saying, because what I'm trying to do here is I'm actually creating confidence intervals. Okay, so I'm creating 95% confidence intervals. And this is like a little too precise. It's not like the greatest thing ever. It's like yeah, it's overly precise, but I like it anyway because it's just an easier way to do it, I think. So I use this function qnorm, and this is going to give me the quantile value from a normal distribution for a specific probability. So when I use 0.025, that's going to return basically negative 1.96. Okay, 2 standard deviations. Qnorm 0.975 is going to give me positive 1.96. Okay, so if you think way back to your intro stats class about the central limit theorem and 95% confidence intervals, that's going to give us the range at which 95% of the values occur under the assumption of repeated sampling. Okay, so what I'm doing here is for my y min value, I'm saying give me the mean city plus that negative 1.96 times the standard error. Okay. And then same thing here, mean city plus positive 1.96 times the standard error of the city. Okay. And that gives us these error bars. Okay. This is messed up though, because these are, we'd have to do something different with those labels. If we wanted to, what we could also do is add the points on there. And I would say you should probably always have the points on there if you're going to have the error bars. But one thing that people do very regularly is they put the points on first and then they put the error bars on top of it. And that can be fine if they're the same color, but very regularly you have like points are, black and then your error bars are gray. And so that can look weird if your points are behind your error bar because you have this gray line going through your point. Okay, so you want to instead put your error bars first, okay, and then layer your points on top of that. Okay, and that looks like this. This I think looks quite a bit better. So here I've just flipped my X and Y axis. And now instead of using geom error bar, I'm using geom error bar H. And then I'm using Xmin and Xmax. Notice I've swapped out my Q norms for just 1.96 on each of these, and I'm doing minus and plus. This is just to show that either way you're going to get basically the exact same thing. The other way is just a little more fancy, maybe. Okay, and this is like a gray color, although it's kind of hard to tell even. All right. So what I would like you to do now is basically do that exact same thing, but using the Palmer Penguins data set. Okay. So I would like you to use the Palmer Penguins data set. It looks like this, right? And then plot the mean bill length millimeters for each species with 95% confidence intervals. Okay, so essentially you're going to create this exact same sort of thing. You could do it horizontally or vertically, it's up to you. But you're going to do the mean bill length millimeters for each species. Okay, 5 minutes, go ahead. Okay, so there are multiple solutions to this, but this is one possible solution. Okay, I'm creating an object I'm just calling MNSE, okay, mean standard error. So I have penguins, I'm going to group by species, and I'm going to summarize, compute the mean and the standard error. Notice when I'm computing the mean, I have to say NA.rm equals true, or I'm going to end up with a bunch of NAs because there are NAs in the mean bill length, okay? Same with the standard error, taking the standard deviation of bill length, dividing it by the square root of n, okay? In this case, rather than computing the lower and upper boundaries within ggplot, I went ahead and just did it in the data set. So I'm saying lower is equal to mean plus q norm 0.025 times standard error, upper plus q norm 0.975 times the standard error, okay? And then I'm doing the mutate here too, so I'm saying my species is factory order species by the mean, okay? Then I'm going to create my plot where I'm saying mean standard error. I'm going to put mean on the x-axis and species on the y-axis. That species, again, right, the factor, it's a factor that's going to be ordered according to the mean. And then I'm going to use geom error bar H, where the x min is equal to the lower and the x max is equal to the upper, right? And then geom point. And it looks like this. Okay, if instead of doing that, I might want to change the height of the bar, because when I do this, especially when there's not very many of them, these just like way too big to me, the error bars. Okay, so instead I would say height equals 0.2. Okay, and then that makes them look more like this, which is more reasonable to me than these behemoths. Okay. If you were not doing geom error bar H, if you were just doing geom error bar, then this would be width is equal to 0.2 instead of height. Okay. Another slight variant that I actually have come to prefer is to just omit that sort of boundary part altogether. So instead of using geom error bar, I would just use geom line range. Okay. And then that works the exact same way. So basically, this line is just going to extend to the lower and upper boundaries of that point. Okay. Let's talk about dodging for a second. So moving away from Palmer penguins now, we're going to be creating a bar chart. Okay, so I'm using MPG again. I'm going to count drive and year, and then I'm going to compute the proportion, which is n divided by square root of n, and then the standard error of the proportion, which is this thing. Okay, so this looks like this. I have, this is just first 6 rows, but 4-cylinder in 1999, 4-cylinder in 2008. Okay, or 4-wheel drive rather. All-wheel 4-wheel drive, 1999, 2008. Front-wheel drive, rear-wheel drive, 1998, 2008. Okay, and so we have the proportion in each of those for each years and the standard errors around those. So I could start out, yep. That's because I used count. And so count is creating a column for me called n. So I'm referring to that count. Yeah, good clarification. Okay, so now I'm creating a bar plot where I'm putting the proportion, or I'm putting the drive train on the x-axis, right? 4-wheel drive, front-wheel drive, rear-wheel drive. And I'm putting the proportion on the y-axis. Then I'm saying geom call, and I'm going to say fill equals factor. By default, these are, we've talked about this before, right? Geom call, by default, it's going to, if you have 2 or more categories, it's going to make them stacked bar charts. And I don't want that. I want them to actually be side by side because I want to be able to make the comparisons between years. So I'm going to say fill equals factor year, and I have to say factor because they're 1998 and 2008, which are numbers. So it's going to see those as numerically different when I want them to be categorically different. Okay. And so I use position equals dodge to get those as separate bars rather than stacked bars. Okay. So that's cool. But what I really probably want to do now is add the standard errors to these bars, right? So I could start by doing this, and you can see it does not work. So I have my geom call, and I say plus geom error bar. I put my y min and my y max times my prop standard error that I had, right? But it's not working, right? They're not going on the bars. They're just kind of there. So we might think, okay, I know what I'll do. I'll say PD is equal to position dodge 0.9. Geom call position is PD. And then for the error bar, position is equal to PD. It still doesn't work, right? And so at this point, you might get really frustrated and not understand why it's not working. And it's just because of this. You have to specify the grouping factor. Okay, so normally you would say color is equal to year or fill is equal to year, right? Because I have that up here, right? I have fill is equal to factor year for the geom call, but I don't have that for my error bar. And so that's why it wasn't moving. Notice we have something else here, though, that's strange, which is we have our error bars extending past 0, right? So we're saying that like we think that there's a possibility that there's a negative proportion of rear-wheel drives, right? Which we know is impossible, okay? So what we can do instead is change our y min so that it is this thing, right? It's that, but if it's less than 0, then it's going to be 0. Otherwise, it's going to be that, okay? And then I changed the width and the height there too, and then it ends up like that. So now these ones, the uncertainty just extends right down to 0, which is the lowest value we can possibly have. And then otherwise it extends up to the top of our uncertainty. Okay, yep. It's right in line. So this is the bottom of the graph right here. But this is the other thing I was going to mention is that this theme, I think, introduces some artifacts here that are like visually weird. And I think it actually is more pronounced here, where it looks like this whole thing is kind of like shifted like this for each one. Like each of these, this vertical line here is really kind of throwing me anyway. It introduces this like weird artifact. So I would actually probably omit those vertical lines if I was going to move forward with this. And then I might put a big thick black line that lays over the top of them right at 0 there. So that is a case where the theming can actually help with clarity, whereas most of the time it's just about styling. Okay, good clarification. Other questions? Okay, this is also, you will see people that say don't ever do these, and like I think anytime people with a few exceptions, I guess, but most of the time when people say don't ever do something, or they say always do something when talking about data viz, like I'm going to generally disagree with that. I think there's a place for most of this stuff. However, I would tend to agree that this is probably not the best way to communicate uncertainty about a value like this. Okay, so we'll talk more about other options here in a bit. The other thing that I think is very important about error bars that is fairly regularly not the case is that error bars are presented, but they are not explained, because error bars can represent a bunch of different things, right? They can, and very often do, represent actually the standard deviation of the data, right? So you can have a point estimate with the standard deviation around it of the data. It can also, as we have kind of seen, represent either a standard error or a confidence interval around an estimate, okay? And so you could have an estimate where it's one standard error on each side, or it could be basically two, which is what we were doing, so it's more of a confidence interval of 95%, okay? And so when you're using error bars, possibly through a caption, but maybe just in text, depending on how you're presenting this, make sure your audience knows what those error bars actually represent, and that they're not just on there without any explanation. Okay, so if they are confidence intervals too, then state the size of the confidence intervals. So very regularly, it's a 68% confidence interval, right? One standard error, or 90% or 95%. So just make sure you're noting that somehow. And one way you can do that, right, is through annotations like we talked about last time, where you could have a point with a standard error, and then you could have a little arrow that points to it, and then just some text that says 95% confidence interval, or 95% of values would be in this range, or something like that. Okay, thinking more about uncertainty. So now we're kind of moving away from error bars, and we're going back to the topic of uncertainty generally, okay? Uncertainty means exactly what it sounds like, right? We're uncertain. We're not 100% sure about the thing, whatever it is, okay? We're essentially always unsure about future events because they haven't happened yet, right? That's obvious. But we're also very regularly uncertain about past events. So this is an example that Matthew Kay uses in his talk, but you know, you look out the window, you see a car at 8 a.m., you get busy working, you look back up at 2 p.m. and the car is gone, right? So you know that the car left somewhere between 8 a.m. and 2 p.m., but you don't know when exactly. And that's a past event that you could have some estimate of, but you're uncertain about it, right? So the question becomes, how do we quantify this uncertainty? Okay, and we usually do this through probability, right? And we have usually some area where we are more confident than the others, and that's why we get this normal distribution of probability, right? But in that case that I just mentioned, like 8 a.m. to 2 p.m., it's somewhere in that range, so that would just be like a uniform distribution of probability between that range. Okay, and so you can think of different types of distributions to describe our uncertainty. Okay, but generally, most of the time, if we can move away from thinking about probabilities and distributions and all of that kind of stuff, and instead just frame it in relative frequencies, it's going to be more intuitive. So again, like thinking back to that election, 28%, right? That's more than 1 out of every 4. Saying 1 out of every 4 is a little more intuitive to most people than saying 28%. Okay. So let's think about framing a single uncertainty. This is an example from our book, but it is also a basically different version of those risk theaters that that he showed us, right? Except instead of actually showing a theater, it's just like a grid of squares, and then we color in the squares according to a specific probability. Okay, and then down here we have some legend that says the darker ones are success and the lighter ones are failure. Okay, cool. So how do we make these in ggplot? I actually just did a presentation last week where I used one of these to communicate the uncertainty in the estimate. I think it's a pretty nice way of doing it. Okay, so what we do is we first just start out by creating a grid, and it could be a 5x5 grid, it could be a 10x10 grid. In this case, I'm doing a 20x20 grid. Okay, and what we do is we use this function from base R called expand.grid. And what this function does is you give it however many values you want, and it's going to repeat those other values for every level of the previous values. So in this case, we only have two things, which I'm calling X and Y. So basically, this X is going to go 1, 2, 3, 4, 5, 6, all the way to 20, while Y is 1. Then it's going to go 1 to 20, while Y is 2. Then 1 to 20, while Y is 3, right? And so we get this data frame in return, where this is what the first 6 rows look like, and this is what the last 6 rows look like. And so you can see overall there's 400 rows, but 20 is staying constant here while X is changing, Y, and so we end up with every possible combination between 1 and 20, okay, for those two values. We can take this now because it is a data frame and we can just plot it immediately. Okay, so I go ggplot, I'm going to plot that grid, put the X on the X-axis, the Y on the Y-axis, and then use geom_tile. Okay, in this case, I'm saying make the color gray 40 and fill it with white. Okay, and then I use theme void because all I'm really trying to do is just see the grid. And there we go, right? We have a grid now. Great. So what's the next step? Well, we need to create an occurrence rate. We want to fill in those squares or rectangles in that last case because I didn't use chord fixed. We want to fill those in a way that is equal to the probability that we're trying to communicate. Okay, so how do we do that? Well, again, like pretty much everything, there's a bunch of different ways, but this is one. Okay, please follow along if you can. Okay, first, so you can go ahead and copy this code and start running it, and I'm going to talk you through it while you're doing that. Okay, first you're going to create your grid. So this is just like I did before. Expand.grid, put your X value and your Y value. So if you wanted a 10x10 grid instead of a 20x20 grid, you just change this to 1 to 10, 1 to 10. Okay, so there's my grid, and then I need to create a instance that I'm going to sample. So in this case, I'm trying to communicate what a 10% probability looks like. Okay, so I'm going to take the number of rows in the grid, which is 400, and I'm going to multiply that by whatever my incidence rate is. Okay, so 10%, 0.10. Okay, so this is the number that I'm going to end up sampling. And the reason I do this is because it's easy to figure out when it's 10%. But what if it was, 23%? Then it's not quite as straightforward. It's still not super hard, but it's just easier to have it calculate it for you instead of you calculating it. Okay, then I'm going to set a seed. The reason I do this, and you can say any number that you want in here, but the reason I set a seed is to make this process reproducible. So I do this now, I come back tomorrow and I run the same code and I'll get exactly the same results. It is a random process. Okay, it's totally random, but this setting of the seed makes that random process reproducible. Okay, so if I said, for example, pick a number between 0 and 100, and I don't set a seed, every time I would get 53, 27, 68, right? It's going to give me different numbers every time. If I set a seed and I say pick a number between 0 and 100, it would give me, 71. Then I set that seed again and I say give me a random number, it would say 71, right? It's a random number, but it's just always starting that random number at the same point. So the random generation process is the same. Okay, so now I've set my seed. I've got the number that I'm going to sample, and I've got my grid that I'm going to sample from. So I'm creating a thing called samp, right? My sample. I'm going to use this function called sample, which is going to do that same sort of thing I was just talking about, the drawing like a random number between 0 and 100. But what I'm going to sample is a number between 1 and the number of rows in the grid. Okay, that's what the seq_len does. Seq_len, a sequence for the length of the number of rows in the grid. So it's the same as doing 1:400. Okay, this just makes it a little more programmatic because you could change any of this up above and this would still work. Okay, so it's going to sample a number between 1 and 400, and it's going to give me back the number to sample, which is n sample. Okay, there's other options that we can add to this, but in this case, I only want the number one time. So after it samples that number, I'm not going to get that number again. So basically, I'm going to get a bunch of these rows are going to be sampled. Okay, so if I just look at my head of samp, I get 318, 134, 180, 283, right? These are just numbers that it's randomly sampling. And the number of those that I'm getting is equal to this in sample. Okay, so in this case, I'm getting 40 samples because I'm sampling 10% of the number of rows in the grid, which is 400. Okay, following me so far? All right. Then from here, I'm going to create a new variable in my data set, which I'm calling event. Okay, because this is just totally generic, right? If it was something different, then I would actually put the name of that variable, right? But here I'm going to say grid, I'm going to say row names to column, and I'm going to say row ID. So that gives me this variable right here. All that's doing is just taking this number and it's making it an actual variable instead of just the row number. Okay, I already have my X and Y. Now I'm going to create a variable through mutate, and I'm going to call it event. I'm saying if else, if row ID, if this number is in my samp, this thing back here, then make it yes. Otherwise, make it no. Okay. And so then when I look at my grid here, you can see with event, it says no, 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 yes. So 5 was one of the numbers that I sampled previously. So I get a yes there. Okay. Now from here, that's all the hard part. From here, it should be pretty straightforward, right? This is just essentially creating a heat map. So we're going to do X, Y, and all I'm going to do is on my geom tile, I'll say fill equals event. Okay, inside my aesthetic, I'm going to make the color equal white, whatever, plus theme void. And you get something that looks like this. Okay, so this is 10% of the cases. This is the event. The coral color is no, and this sort of teal color is yes. So that's fine. However, we probably want to customize it to make it look nicer. So I've given you some code here that I think is kind of nice, because what we're going to do is we take just a single color that we like, right? So here is the color that I've decided on. This is, from like HLS Picker or something like that. And what I'm going to do is I'm going to lighten this value by 50%, and I'm going to desaturate it by 70%. Okay, so that's going to be one of the colors, and then the other one is just going to be that color. All right, these values, 50% and 70%, you might have to play around with depending on the color that you choose, but it gives you a good sort of place to start, and then you end up with something that looks like this. Okay, so here I have now, did the event occur, yes or no? And you can see the blues are the yeses, so there's your 10% rate. So make it all of these lines white. Yeah, so that is color equals white right there. And then I got theme void in there too, which helps take all the other stuff out of it. Other questions? Okay, you could also do it the opposite way. So now we're saying chance of rain. I don't remember what I said the rate was, I think 80% or something like that. So this is like the opposite, where it's like, whoa, that's a lot of blue, right? You can also consider varying the grid size. So this is 10 by 10, 20 by 20, 30 by 30, right? And so the optimal grid size is probably going to depend on your venue and how big the thing is, right? But this is getting pretty small. So I tend to like more like 20 by 20 or maybe 10 by 10. Okay, 10 by 10 I think actually looks really nice. The only problem is it can't be super refined, so you can't get like 42% or whatever very easily, because it's going to be rounding essentially. I mean, it's not rounding, it's a random process. It's 42% of the time, whatever. But okay, so I'm going to actually skip this. I would love if you could come back and do this later, but we're not where I'd like to be at 3:10 today on Monday. Okay, so I'm going to go ahead and just skip this for now. All right, let's talk about non-discrete probabilities. So we're going to go to hypothetical elections again, okay? And let's say there's a blue party and a yellow party, okay? And the blue party, based on the polling that we have, we're saying that they have a 1% advantage, okay? But the margin of error that we have is 1.76 points. So in this case, we could collapse this to a discrete probability where we would say, you know, who's going to win, blue or yellow. But very often we want to know not just who's going to win, but by how much, okay? So this is basically what our distribution looks like in this case, okay? So down here on the x-axis, we have our percentages, okay? And this is our best estimate, this 1 point advantage. It's actually 1.02, I think. 1 point advantage for the blue party, okay? And so this yellow party, there is a chance that they're going to win, right? And so we want to know what's the chance of a really big blue victory or a yellow victory or possibly even like a fairly big yellow victory. I mean, not super big here, it wouldn't look like, but. So how do we do this? Okay, well, there's a bit of math involved here, okay? This distribution back here is defined by a mean of 1.02, okay? So that's the actual difference. That's this point, this like peak of the distribution, okay? And then it's got a standard deviation of 0.9, okay? Which is, you know, 1.76 times 2, basically, okay? So what we're going to do is we're going to say, okay, well, what's the chance that the end result is below 0? Yellow wins. And we can do this a couple of different ways. Okay, so I am, at least for the moment, only collapsing it down to that dichotomous decision, which party wins. So we can calculate the exact probability that yellow wins. And the way that we do this is not very easy. It's fairly, I mean, it's not horrifically complicated, but it's not super straightforward either. Okay, what we're going to do is we're going to create some sample data. This is just a whole bunch of points from -5 to +5 in increments of 0.001, right? And then I'm going to calculate what's the likelihood of that event occurring, given that we think the data come from a distribution with a mean of 1.02 and a standard deviation of 0.9, okay? And that's what this is right here, right? This is all of those little points from -5 to +5. This is the likelihood of them occurring, okay? And so you can see -5, that would mean that the yellow party won by 5 points. That's almost a 0% probability, right? Basically is. But these ones over here, like there is some actual density under this distribution where, you know, the yellow part could win. So what we want to do is we want to calculate this portion, right? From 0 over, what's the total sum of that area, okay? So we can do that through integration. This is a package that does some XY integration. And so I'm just limiting my data to those cases where it's less than or equal to 0. And then I'm summing the likelihood, basically, is all that's happening there. And I get 0.129. Okay, so about 13% chance. We can also do that, though, in a much easier way by just simulating. Okay, so here I'm simulating 10,000 draws from a random normal distribution that has a mean of 1.02 and a standard deviation of 0.9. After I've taken all of those random samples, then I'm going to say, okay, how many of those are greater than 0? And so we get basically the exact same result, right? About 13% are not, and the rest of them are. Okay, so this is telling us there's about an 87% chance, if we were to reduce this to a dichotomous decision, there's about an 87% chance that the blue party would win and about a 13% chance that the yellow party would win. Okay, so that's all fine, right? And some of that was kind of just in the side, but as we've talked about earlier, we're not great at interpreting probabilities, and we're not great at all of inferring probabilities from a density like that curve, right? We're not very good at that. So how do we actually create this? Like, what do we do from here? How do we communicate to people not just which party's going to win, because if that's all we were going to do, we could go back to that risk, those risk theater plots, right? Now we've got our probability 13%. We could create a plot that shows 13% with that risk theater sort of approach we just did. However, if we're instead interested in how much, then what we can do is we can create these things, and this is very new, right? And these have not really taken off, but I think they're very neat, and so that's why I'm showing them to you. Okay, and I do think they would probably take a little bit of communication if you're trying to communicate them with a scientific audience. They're actually probably going to be more interpretable for a less scientific audience than a scientific audience who's used to seeing things like densities, because this is not a density. Okay, so what we're going to do instead, okay, is we're going to discretize this. Okay, so we have all of our probability ranges from 0 to 1, right? 0 to 1 is our probability space. And what we can do is just take some equally spaced intervals from 0 to 1, and then we can calculate the probability within those intervals. Okay, so in R, there's this p points function, okay, probability points. And all it really takes is this one argument that is saying the number of points. And you can see what it does is this is going to give me 50 points spaced equally between 0 and 1 for different probabilities, right? So in this case, it's just jumping up by 2 every time, right? 0.01, 0.03, 0.05. But you could also give it a number of 25 or whatever, any number you want, and it'll give you those equally spaced intervals. Then from there, we can use Q norm, which we saw way back at the beginning, right? And we can say, what's the probability of these values under a distribution that has these properties, okay? So our distribution that we had before, 1.02 and 0.9, okay? And so this is going to then transform these probabilities into these actual estimates. Okay, so these estimates are the actual estimates of the amount that each party would win by. Okay, so we're saying there's about a 1% chance that the yellow party would win by 1.07 points. Okay, there's about also a 1% chance that the blue party would win by 3.11 points. Okay, so let's look at this now, how we can plot this. Okay, so we're going to take this Q norm on our PP points. Okay, and these are on the actual metric that we're looking at here now, which is percentages. We're going to put that as our x-axis, and then I'm going to say mutate to create a column called winner, where if it's less than or equal to 0, I'm going to call it this color, which is a yellow color. And if not, it's going to be this color, which is a blue color. Okay. And so I can look at this for the head. It's all this color to start, right? And then after it crosses 0, then it changes to this color. All right. And then what we can do is we can start to plot these. So here is a plot where each of these little balls represents basically a 2% chance of a value in that range occurring. Okay, so I use ggplot, I put x on my x-axis, and I use geom.plot. Okay, and obviously we're going to continue with this, but what I can do then is say now fill equals winner, and you can see basically once it crosses 0, then it's going to change the value. But one thing that's interesting about these is that they actually have a bin width, just like a histogram does. And that's going to bin values on the x-axis. So you can see there's quite a bit of space between these two, but there's also like a lot of space up here. And so I probably want to collapse that some so that it's a little more clear here. So what I'm going to do is I'm going to change my bin width to 0.35. So notice that gap between these two is now reduced, right? But at the same time, those balls are becoming greater. And so now we have that same sort of distribution like we had before, but we've discretized it so that we have all of these individual like balls basically, and rather than all of them. Yep.
In this step just before this, where you were creating the winner column, are these values for color actually exactly the ones that are, because couldn't you just have like winner, loser?
Yes.
And then fill equals winner?
That's exactly right. Yes.
Okay.
Yeah, I'll show you why I did it this way. It's just this is one of those examples where like I'm showing you kind of another way to like another little trick basically. So yes, normally I would probably also do you know, blue wins or whatever, like some text, and then I would do scale fill manual, and then I would put the values I want. In this case, I'm doing that because so you can see the legend here has those values, which is like dumb, right? That's totally not interpretable. But what I can do is, we'll get there in just a second. So here now I'm just annotating this a little bit. So I have this vertical line here, okay? And then this is the part that I was going to get to. You can use this scale fill identity, and it will just actually fill those values with whatever the column value is. So that's why I did that. Yep.
Yeah, you mentioned that each ball represents 2% probability. Is that because of that?
Because there are 50 of them. Yep. Yep, that's exactly right. Because there are 50 of them. And so, yeah, so now I'm doing a bit of extra stuff, but now you can see that this is now like a discretized version of that density. However, I created all of that, and then I pretty much immediately thought, well, that's probably too many of them, because this is now starting to approximate a density anyway. And so I don't know how helpful that is. In fact, according to Matthew Cave, once you get too many of these, it doesn't work any better than a density. And so what we can do is do this again, but in this case, I'm only using 20 points. Okay, so now each ball is going to represent 5% probability instead of 2%. And notice I've actually put that in the caption here. And so then we get something that looks like this. And this is actually, I think, a very nice way of communicating it, because you can kind of see like, oh, you can see like the total number of balls there, and you can see only 3 of them are blue, right? And the actual probability isn't 15%, right? We know that because we calculated it. It's closer to 13%. So it's a bit rounded here, but it still gives you a good idea of what it is. And you can see like, yeah, there's actually some chance that yellow is going to win by 2 points or even 3 points, right? Whereas the blue, like most likely if they're going to win, it's going to be right close. There's a small chance that it'll have a larger victory. Okay, questions on that? This is like really different, right? This is probably the most like non-standard thing that we'll talk about here. I really haven't seen these much out there outside of Matthew K and a few other people that he works with, but I think they're really neat, which is why I'm showing them to you, and I actually have you produce one during the homework. Okay, so no questions on that? All right. So we've talked about for a single value now and for discrete things and non-discrete. Let's talk about point estimates. So really quick, hopefully review. What is a standard error, right? A standard error is the standard deviation of the sampling distribution. Okay, well, what is the sampling distribution? The sampling distribution is the distribution of the samples from the underlying population-based distribution, okay? So whatever distribution you think the data were generated from, if you were to pull repeated samples from that, that's the sampling distribution, okay? So what does this mean? Let's actually simulate to explore. This is my favorite way to get to know what these things mean and what a sampling distribution is, what different distributions look like, etc. Okay, so let's just assume a normal distribution and that we have some real distribution that we know. The population distribution, the actual real distribution, has a mean of 100 and a standard deviation of 10. All right, cool. So let's draw 10 samples from that distribution. We can do that in R very quickly with R norm. So I'm setting the seed so it's reproducible. We'll say n equals 10, draw 10 samples from a distribution that has a mean of 100 and has a standard deviation of 10. Okay, so when I do that, these are the actual values that I get from that distribution. I could do something like calculate the mean for that. And you can see that my mean for my sample is 101, which is slightly different than the actual mean, which is 100. Okay, so we could do it a second time, do the exact same thing. And this time when I call the mean, I get 102, actually slightly more different than the actual one, right? But if we do it over and over and over and over and over again, then we'll see that the mean of these means is equal to the population mean, and that is the central limit theorem. So here's, I'm saying do it 1,000 times, pull 10 observations from this distribution. Simplify equals false just means give me a list back instead of a, I don't know what it gives you, a matrix maybe. So I'll say calculate all means. And so what I'm doing is I'm going to loop through each of these. For every one of these, I'm going to calculate the mean. And then it looks like this, right? So these are all the different means. So the first one was only 95.8. The second one was 103.2. Third one was almost exactly the population mean, 99.9, right? So the standard deviation of these means, that's the standard error. Okay. So we can calculate that by saying, what's the standard deviation of those means? And we see it's 3.14. Okay. If we were to calculate the mean of those means, that would be basically 100, which is our population mean. So that time we were pulling with a sample size of 10. Let's do the same thing again, but this time we'll use a sample size of 100. Okay. So this is all the same stuff, but now we've got a sample size of 100. When I look at my standard error now, it's 0.97. So when we had only 10 observations per sample, we had a standard deviation of 3.14. When we have 100 per sample, we have a standard deviation of 0.97. Okay, so basically, the larger our sample, the lower our standard errors. Okay, so hopefully we know all of this. We can look at these distributions. Here I'm just saying the iteration, I'm looping 1 to 1,000 twice, or repeating 1 to 1,000 twice. And then I'm saying what's the sample size? So it's 10 for the first 1,000 times, and then it's 100 for the next 1,000 times. And then we're getting the means for each of those. Okay, so here's the means for all of them. And then this is the distribution of those means. Okay, so you can see for both of them, they pretty much center right on 100, which is what we would expect, right, given the central limit theorem. But the spread of those means is going to depend on the sample size, and the standard deviation of this distribution is our standard error. Okay, so all of that is cool and fine. That's the review part. Now, at least I hope it's review. Now we're going to jump to a model, because very, very often it's hard to talk about visualizing uncertainty without talking about a model, right? Most of the time when we're talking about visualizing uncertainty, we're talking about visualizing uncertainty in an estimate from a model that you have fit, right? So here now we're going to actually fit a model, and we get these standard errors, right? And these standard errors are the estimate of this, between sample variation. It's essentially, it's the standard deviation of the sampling distribution. In this case, these are two sampling distributions. Okay, so what we want to do very often is visualize those estimates with their standard errors. Okay, so again, this is not like a modeling class, so we're not going to get too deep into this. But one of the things that is very nice is this tidy function from the Broom package. Okay, and I can tidy m, which is my model I fit back here, right? Where I'm saying, give me the confidence interval back. Conf.int equals true. And what it will do is it will return a data frame for me with the estimate, the standard error, the statistic, which is going to be a t in this case, it could be a z or a f or whatever, p-value. And I don't really care about any of that stuff. What I really care about is the conf.low column and the conf.high column, okay? Because we can use those when we're visualizing our uncertainty of these estimates, okay? So this is very standard. This is what Matthew K talked about as sort of like just almost a throwaway, like, this is an alternative to a table, basically. But I still think it's actually pretty nice, right? I have chord flip on here, so this is all kind of backwards. But basically, we're going to use geom error bar, where we just say the y min and the y max are equal to those conf.low and conf.high values. Okay? And so then you can see we have our intercept, which is usually going to be all the way out here. Sometimes we might want to actually drop the intercept before we plot it like this. But in some cases like this, where it's not too far out there, it's probably okay to keep it on there. And then you can see the estimate with the standard errors, and that's fine. Another alternative, though, and this is all of that background was to get to this point. This is what I would consider a non-standard way of showing the uncertainty that is also like very much in the standard realm. So I don't think you're going to get very much pushback at all from people for doing this. And I think it's a really nice way to communicate the uncertainty. All we're doing here is instead of just having this one standard error or this one confidence interval, I'm going to plot multiple confidence intervals. Okay, so I have my tidy data, right? But when I create my geom error bar, I'm going to first start with a 95% confidence interval. So I use Q norm 0.025, Q norm 0.975, right? The difference between those is 0.95. That's our 95% confidence interval. And then I'm going to say for the color, right? Notice across these, I'm using the same color all the way, except I'm lightening these. So this one's going to be my widest, right? So I have this one at 0.6. I'm going to lighten this one 60%. I'm going to lighten this one 30%. And then I'm just keeping this one this color. Okay. And so here I have my 95% confidence interval. Here I'm going from 0.05 to 0.95. So that's going to be a 90% confidence interval. And then here I'm going from 0.1 to 0.9. So that's going to be my 80% confidence interval. Okay, so I'm just layering these confidence intervals on top of each other, one after the other. Okay, then I'm going to layer some points on there, and then I have chord flip because this is older code. And it ends up looking like this. Okay, again, I would argue that this is a significant improvement over the last one because it gives you sort of a fading out, basically, of how likely the points are. Okay, and that happens through two things. One is the multiple confidence intervals, but the other is the fading of the color, that color getting lighter and lighter as it goes out. Okay, so this is, I think, very much in the realm of like standard, but it's like just one additional step that I think actually helps communicate that uncertainty better. And if nothing else, it's going to get people to pause for a second and be like, oh, what is that, right? Again, though, it's very important that you communicate what these confidence intervals mean. The other thing that we want to do is, in this case, as I just said, we want to communicate what these confidence intervals mean. We don't have any legend. We don't have anything, right? We don't have any way of communicating what this is. So there are ways to do this. I think I've shown this before. It's a little bit hacky, but I think it works. Well, it does work. I mean, I don't think it works. I know it works. But it just feels a little bit uncomfortable because it's a little bit hacky. I don't know how else to describe it. Okay, so what we're going to do is I'm going to say inside of my AES, right? I'm going to say color equals 95% and color equals 90% and color equals 80%. Okay, that's inside of my AES for all of these. Okay, we don't have a column that is called 95% or a column called 90% or a column called 80%. So what it's going to do is it's just going to go to the default first color, default second color, and default third color. Okay, and then it's going to label them like that. Okay, so there we are. But then all I have to do to fix this is say scale color manual, put my name as something better because before my name was color. Right? So I'm going to put the name as confidence interval. And then for my values, I put those three different values I have. Okay. And then we end up with this. Okay. 80%, 90%, and 95% confidence intervals. All right. Mm-hmm. Yes. Yeah. So the question for those of you on Zoom, if you couldn't hear, was that the colors are going darker to lighter. And the question is basically, is that what we want to do essentially all the time, right? And I answered yes, because basically darker values, just like a heat map, right? If you think about a heat map, like dark values mean more data, right? And in this case, we're not trying to say more data, we're trying to say more likely, right? And so we want to fade from dark to light, because those lighter values are saying like there's less chance that it's out in these areas. Good question. Other questions? Okay, another idea, and this one is absolutely non-standard, but I think they're really neat, are these things called density stripes. Okay, and so for these, we have to install a new package, this Wocolab Ungiviz. I don't know how you say it. That's how I say it, Ungiviz. And so I'm taking my same data frame here, right? I'm putting my estimate on the x-axis. Wait a minute. Yeah, my estimate on the x-axis, and then my term on the y-axis. But then I have this new function that comes from this package called stat confidence density. Okay, and I have to feed it this MOE argument, the margin of error. Okay, and so I'm just going to tell it the standard error is the margin of error. It's going to do the rest of the calculations for me, and then I can give it a fill color if I want. And what it's going to do is it's basically going to put a bunch of stripes, just little lines in there, and those lines are going to they're going to kind of fade out as it becomes less and less likely. Okay. The other thing that we can do also from this is from ggridges, is we can use stat confidence density. We can actually plot the actual densities of these things rather than the density stripes. Okay. I actually prefer the density stripes, but either one, they both help, right? And they're both just alternative ways of doing this. Okay. All right. Let's see. We only have about 10 minutes left. So let's just, I know this is like a lot of me talking today, and I apologize, but we're going to skip that too, because we need to get at least through the uncertainty stuff today, which is just a few more slides. So if you have time, I think you probably should come back and do these two practices that we missed, but obviously if you don't have time, that's fine too. This is stuff that is in the homework though, so you'll have to practice it that way regardless. Okay, and then, yeah, so just sort of the last thing, that first one that I talked about in the homework, right? It has a geom line range is what it is. And then I ask you to reproduce it using a non-standard one. I would probably expect either like this or this or this, right? One of those three options, most likely. Okay. All right, HOPS, hypothetical outcome plots, and some related plots. Okay, so when we have a regression plot, it typically looks like this, right? This, at least in ggplot. We have something on the x-axis, something else on the y-axis, and then we put a layer of points, and then we'll often layer a smooth on there. Sometimes we'll say method equals LM to make it a straight line instead of this curvy line, but it's the same sort of thing, right? And what we have to communicate our uncertainty is this gray area here, right? That gray area is telling us where we think, we're less certain about what this line actually represents. An alternative is just to do something like this, okay? And so what we're doing here is we're actually computing a bunch of different regression lines and then just plotting all of them, okay? And so this is a form of a hypothetical outcome plot because none of these are the actual line. But that's kind of the point, is that this isn't actually the actual line either. It's an estimate of the line, right? And this gray area, rather than having this shading, we can just have a whole bunch of lines to show the same sort of thing. Okay, how do we do that? We do it through bootstrapping. Okay, so again, many different ways that we can do bootstrapping, and in fact, through the ungviz package, there are some functions that will help you with that. So if this is like a little more manual, and I've done it this way to try to help communicate what's happening when the bootstrapping is happening. But if you just want to bootstrap and you don't want to actually go through all of this practice or all of this code, just go ahead and use, I think it's just called bootstrap from the ungviz package, and you can feed that within a function, right? So we can look at that together if you want at a different time. All right, but in this case, I'm going to say I want 100 bootstrap resamples. So what is bootstrapping? Bootstrapping is basically, I have a data set, right? And I'm going to sample rows from the data set, but I'm going to sample those rows with replacement. So I sample the third row and I miss the fourth row and I get the fifth row, but maybe I get the fifth row actually 3 times. Okay, not even just twice, but maybe I get it 3 or even 4 times. But the fourth row isn't in there at all. Then I get the fifth row twice, the sixth row once, don't get the seventh row at all, right? So I'm sampling like that. Each time I sample with replacement and I calculate a new regression line. Okay, that's what bootstrapping is. And then if you do this enough times, then you'll get an estimate of the sort of variability in these estimates. Okay, so I'm going to use this function replicate. I'm going to say replicate this 100 times. I'm going to sample a sequence of numbers from 1 to the number of rows and empty cars. And then I'm going to say replace equals true. Okay, and then how many I'm pulling out is n row cars. So let's say cars has 52 rows, right? This would say sample the numbers 1 to 52 times with replacement. Okay, so pull a sample of 52 from the numbers 1 to 52 and replace equals true, right? So some numbers will be in there multiple times, others won't be at all. Okay, so this is the first one, right? So for you can see in this first one, there's 22, there's 22. We got 1 represented multiple times, right? But then some of the rows are by definition not in there, because if 22 is in there twice, then obviously at least 1 row is missing. Okay, and then we do the same thing down here. There's 8 represented 3 times in this one. Okay, and so by definition, other rows are left out. And then for each of these samples, we're going to fit a regression line. So it looks like this. Okay, this code is again more manual, but I'm going to say go through that row samps thing I have back here and give me just the data for those rows. Okay, this is again, don't worry about the code so much. I'm trying to get the conceptual part of this. So give me the rows that have these numbers. All right, and so sometimes this is going to be repeating, right? So like right here, we have Pontiac Firebird, right? And so that row of the data set is repeated. Okay, now once we do that, we are able to create this plot where we have this dsamps thing back here that I'm creating, right? And I'm going to say that's the data source for this stat smooth, but I'm going to say the group is equal to the sample. Okay, so here's that sample column. Okay, and then geom is going to be line. Notice I'm making the size very small, and then I say full range equals true, so it's going to extend it all the way from the thing, and then that's how we get that. Okay, that is fairly fast, and there's absolutely code in here that we have not covered with mapdf and replicate and other things like that. But what I'm trying to get you to see is the process of taking a data frame and one sample, right? This is one sample, and this is the second sample, and it's just basically pulling a bunch of data frames like that. So it's a way to sample from your own data frame and then fit that over and over again like that. Okay. Now, if we were able to plot that with our standard error that we had already estimated, we would see that they actually overlap almost entirely, right? And so that is good evidence that our bootstrapping method is working as we expect it to. But it also shows you that whether you show it like this or you show it like this, you're showing basically the same thing. Okay, it's just alternative ways of showing it. And I think this is actually preferable because in large part, your eyes don't fall on one specific line and try to interpret that one line as the value. Okay. The real hop part of this, though, comes from this, actually animating the process. Okay, so the point of this is very much the same as what I had said before, where this doesn't allow your eyes to sort of rest on an individual line as the line. And so it animates it. Okay, this is the code to do this with GG animate through transition states. Again, we can do the bootstrapping easier. I will try to find the code to do that through UngiViz and I'll get it to you. Okay, so you can do that on your own later. This is another example where we're looking at chocolate ratings between the US and Canada. Okay, and so I think it's Canada has higher chocolate ratings overall than the US, but you can see based on the number of points, right, they have not nearly as many chocolates that are being rated either. So these lines are randomly pulling one value from Canada and one value from the US, and you can see how often like the US is higher versus Canada, or the Canada one is higher than the US. And this is sort of the point of this is sort of to show that there's a lot of variability in this too. And so even though the mean might be slightly higher, that doesn't mean a whole lot for one randomly chosen chocolate bar from each country. Okay. All right, last thing I want to show is Dr. K again. We've only got 2 minutes, so that's perfect. And then we'll close out for the day.
So going back to the election data, just to sort of finish up, because that seems to be the way to finish up. This is, of course, the New York Times election needle. What I really wanted to have on this slide was the New York Times election needle for the midterm. So I had this whole plan where I was going to sit and like record the entire thing over the midterm, and then they turned the jitter off. So I have to use the old version because I like the jitter. People don't like the jitter. So my favorite one of these, down here in the right-hand corner, the New York Times needle jitter is irresponsible design at best and unethical design at worst, and you should stop looking at it. I completely disagree with this. I was actually really sad that they got rid of the jitter. The jitter is essentially hops, right? And it is forcing people to confront their uncertainty in these predictions. And so people got angry and they got anxious and they got frustrated. But I think they got angry and they got anxious and they got frustrated because they should have been. If you're uncertain about something that you care about, you should be anxious. And so that actually kind of just brings me to the end of my talk, which is that I think that what we need to do in uncertainty visualization is present well-calibrated uncertainty that can't be ignored in ways that people can actually understand. Thank you.
All right. So I'll end there. But I totally agree with what he's saying there. If you care about something a lot and there's a lot of uncertainty about it, then you should present it in a way that there is a lot of uncertainty about it, because that's actually much more truthful, right? And so people really hated that thing and they ended up getting rid of it because there was too much pressure on it. But I agree with him totally. That is actually a better way to communicate it, because yeah, people got anxious about it because they cared about it a lot and because there is actually uncertainty about it. It's not a firm estimate, right?